This is Chapter 5, the normal curve, continued. We're going to talk about standard units. Standard units say how many standard deviations we are above or below the average. If we're above the average, it's positive. If we're below the average, it's negative. To convert to our standard units, we're going to use the simple formula, where z equals x minus the average divided by the standard deviation. So again, we just have to minus the average and divide by the standard deviation. And that tells us how many standard deviations we are above or below the average. So for example 41, heights of a group of women follow the normal curve with an average of 63.5. So I'm just going to abbreviate it, average of 63.5 and a standard deviation of 2.5. And it told me that it's a normal curve. We want to convert all of our following to standard units. So the first one is 66 inches. So z is going to be our value of 66 minus our average of 63.5 divided by our standard deviation of 2.5. This gives me -1. This means that I am 1 standard deviation below the average because z is -1. Our next one, 61 inches. So z is 61 minus 63.5 divided by 2.5. This is, 66 minus 63.1, that's a positive 1. So we're 1 SD above the average. But for number 2, 61 minus 63.5, that's the -1. So we are 1 standard deviation below the average. For 63.5, well, we do 63.5 minus the average of 63.5 divided by the standard deviation of 2.5, which gives me 0. That makes sense. I'm 0 standard deviations above or below the average, which makes sense because 63.5 is the average. And let's see, for 58.5, so 58.5 minus 63.5 divided by 2.5, I think that would be -2. So that's 2 standard deviations below the average. And number 5, 62.25. 62.25 minus 63.5 divided by 2.5 gives me -0.5. So that means we're 1/2 standard deviation below the average. To help you visualize this, I have this diagram. So these are the actual heights in inches. So the actual heights are this block histogram. Those are the actual heights. And we said they're pretty close to a normal curve, and so we've kind of overlaid the normal curve. And you can see that it's fairly close, but not exact. Also notice that the scale underneath it, so we have height in inches, 63.5, 66, 68.5, and then underneath it we have standard units. So 63.5, that was mapped to 0 units because that was the average. 61, that was -1. 66 went to +1. 58.5 went to -2. So basically for standard units, we just change the scale until we get to our standard units. After we convert every number to standard units, then our new list of data values would have an average of 0 and a standard deviation of 1. Or if we convert to standard units, then we have a standard normal distribution. Now we might want to reverse our standard units. To reverse our standard units, we just rearrange that equation, where remember z was x minus the average divided by the standard deviation. So if you just rearrange it, you multiply by the SD, you add the average, you'll get back to x. And people always ask me, what does x actually represent? What is the x? So x represents the original data, or if you want to think about it, the real world numbers. So in our last example, when we were talking about heights, x would be going back to the heights. Or in example 42, test scores have an average of 70 and an SD of 10. So the test scores would be our original data or real world numbers. Let's see. Okay, so we have an average of 70 and an SD of 10. So number one, if a student scored 1 in standard units, so that means they were 1 SD above the average. What is their actual test score? So we want to figure out their test score. We know that they're 1 SD above the average. So if they're 1 SD above the average, we can say, well, what is the average? And add 1 SD. So my average was 70, and I want to add 1 SD, which was 10. So their actual test score was 80. Number two, if a student scored 1.3 in standard units, what is their actual test score? So that's 1.3 standard deviations above average. So x is going to be the average plus 1.3 standard deviations. So 83. So I just think of it as, okay, so it's 1.3 standard deviations above the average. I just add 1.3 standard deviations to the average. Or you can just look at the formula. So average plus z, which is the 1.3, times the standard deviation. Because this just means that z is 1.3. So number three, if a student scored negative 2.1 standard units, what is their actual test score? So that means that z is negative 2.1. So we're 2.1 standard deviations below the average. So if we're below the average, it's going to be the average of 70, but then we have to minus 2.1 standard deviations, which is 49. And just the final remark, again, remind yourselves that x represents our original data, our real world numbers, and z represents our standardized units, how many standard units you are away from the average. Now let's talk about the normal approximation. So if the histogram for our data values looks like a normal curve, we can estimate the percentage of people in an interval by first converting to standard units, and then two, using the standard normal table. What we're going to do is we replace the true histogram with an approximate normal curve to give an approximate area. So for our women's heights, technically the women's heights are this blocky histogram. So if you see the actual blocks, these are the true women's heights. But we can replace it with a smooth normal curve, and that will give us fairly good approximations. And then we'll change all of our heights into our standard units. So the 61, that's 1 standard deviation below the average, or 66 is 1 standard deviation above the average. 68.5 is 2 standard deviations above the average. So let's actually try to use our normal curve to find percentages. So women aged 18 to 24 have an average height of 64.3 with an SD of 2.6. And their histogram looks like a normal curve, or at least pretty close to a normal curve. Estimate the percentage of women with these heights. So number one, we want to see the women that have heights below 65 inches. The first thing we're going to do is standardize. Find the standard units. How many standard deviations are they above or below the average? So it's going to be, let's write our formula up here. Z equals the average Z equals X minus the average divided by the standard deviation. So again, X minus the average divided by the standard deviation. So X is 65 minus my average of 64.3 divided by my standard deviation of 2.6. So this gives me 0.269. So I'm saying, okay, Z is 0.269, and I want the percentage of women that are below that. So basically, we want the area to the left of 0.269. This is why we practice using the standard normal table. So we go to my normal table. I'm looking for a Z is 0.26. Notice I can't get Z exactly 2.6. So we're going around to Z equals 0.25 to use the table. So I rounded, and this area to the left was 59.87. So 59.87% of women are below 65 inches. And that's how we do it. So first we found our standard units, we standardized, and then we used our normal table to look up the area. So let's do number 2. We want to know how many women are between 61 and 66 inches. The problem with this is there's 2 different X values, so we have to find 2 different Z values. So again, it's X minus the average divided by the standard deviation. So my first X value is 61 minus my average of 64.3 divided by 2.6, which is negative 1.269. And I'm going to say that's about negative 1.25, so I can use my table. Now let's find my second Z. So it's going to be 66 minus 64.3 over 2.6, which gives me 0.65. So those are my 2 Z values. So now I'm really looking for the area between 0.65 and negative 1.25. I want the area in between. So remember how we find the area in between 2 numbers. We find each area and subtract. So let's go look up my 0.65 area first. It has an area of 74.22. 74.22% minus, and now look up your negative 1.25. So that's 10.56. Which gives me 63.66%. So that's my final answer. And I could say that about 63.66% of women are between 61 inches and 66 inches. And let's try number 3. We want to find the percentage of people that are above 72 inches. One of the things to keep in mind is really we're looking for the percentage that are above 72 inches. So I'm looking for the area to the right of this. So this is our actual heights. And I don't graph this one all the time because all I really need is then to regraph it with my z, or my standard units. So for z, we need to figure out what z value correlates with that 72 inches. So what is this z value? So that's what we want to figure out. So z is, again, x minus the average divided by the standard deviation. So 72 minus 64.3 over 2.6 is 2.9615. But my table only has z's in increments of 0.05, so let's round that to about 2.95. So I can come back over here and say, okay, z is 2.95, so finding the area to the right of 72 inches is the same as finding the area to the right of z equals 2.95. And now we can go use our z table, look at 2.95, scroll down just a little bit, 2.95, it looks like the area to the left is 99.84. So the area to the left is 99.84. We want, though, the area to the right. So we are going to use the fact that everything adds up to 100%. So 100% minus 99.84% gives me 0.16%. So about 0.16% of women are above 72 inches. That makes sense. That's 6 feet, and there's not very many women that are above 6 feet. Our next problem, test scores have an average of 65 and a standard deviation of 15. So, number one, what do you need to know before you can find any percentages? It turns out that you have to know if the data is normally distributed. Because if it's not, you can't use the normal curve. So you need to know that, and as the person with the data set, I'm telling you it is normal. So we can go ahead and find the percentages. Otherwise, again, you can't use the normal curve to find percentages if your data is not normally distributed. Number two, what percentage of students scored between 50 and 60? That's those two different x values, so we need to find two different z values. So for my first z, it would be x minus the average divided by the standard deviation. So my x is 50 minus my average of 65 divided by my standard deviation of 15. That gives me -1. For my second z, it's again x minus the average divided by the standard deviation. So 60 minus 65 divided by 15 gives me -0.33. And I'm going to have to round that to use my table. Let's round that to -0.35. So here's my -1, here's my -0.35, and I want the area in between. Now if I look up -0.35 on my normal table, that's 36.32, but that's the area all the way to the left. So that's the area from here all the way over. But I didn't want that area. I only want the area in between the two numbers. So what if we look up the -1? It's going to tell me the area from -1 all the way over. So -1, that's 15.87. So how do you find the area in between? You just subtract. So 36.32 minus 15.87 gives me 20.45%. So about 20.45% of students scored between 50 and 60 points. And number 3, what percentage scored over 80? So we're just following our exact same procedure. Z is again x minus the average divided by the standard deviation. So my x is 80, the average is 65, my standard deviation is 15, so this gives me 1. So z equals 1. I want the area to the right because I wanted the percentage over 80. So if I go to my normal table and I look at +1, that's an area of 84.13, but I don't want the area to the left, I want the area to the right. So I'm going to have to subtract that from 100. So 100 minus 84.13 is 15.87. So that's my final answer. What does this truly mean? That means about 15.87% of the students scored over 80. The next thing to talk about is percentiles. Percentiles are useful for summarizing spread, and this actually works for any distribution, not just normal distributions. So the pth percentile, the way we define it is that it has p% of the area to the left of it. So like the 10th percentile, that just means it has 10% of the area to the left of it. 25th percentile has 25% of the area to the left of it. 75th percentile has 75% of the area to the left of it. So the 50th percentile, 50% of the area to the left, means there's 50% to the left, 50% to the right. That sounds familiar. That's what we called the median back in chapter 4. So now let's be more specific. Let's find the percentiles for the normal curve. We can find percentiles for the normal curve by using the table to find standard units. So this says how many standard deviations you are above or below the average. And then number 2, reversing the standard units to get to our percentile. And again, we're going to use that same formula we used once before, where x is the average plus the number of standard deviations, z, times the standard deviation. So let's try this. Example 47. Women age 18 to 24 in the Haynes study have an average height of 64.3 and a standard deviation of 2.6. The histogram looks like the normal curve. Estimate the 30th percentile of these heights. So number 1, we're going to use the normal curve to figure out what z is, or how many standard deviations we are above or below the average. So if we're looking for the 30th percentile, then that means there's 30% to the left, and we're looking for the z value that gives us that. So I go to my normal table, and because the 30% is an area, I look in the area column for 30%. And it looks like this -0.5 is pretty close. So z is -0.5. What does that tell us? That means, so the 30th percentile is 1/2, -0.5, standard deviations below the average. Now let's figure out what height that would actually represent. Remember, x is going to be our average plus z times the standard deviations. So in this case, x is our average of 64.3, But then we have to minus because z is negative, where half is standard deviation below the average, and my standard deviation is 2.6. So x is 63. So the 30th percentile is 63 inches. Example 48. Test scores follow the normal curve with an average of 65. And a standard deviation of 15. And it tells us that it follows the normal curve. So we can use the normal table to do everything. Number 1. Find the 60th percentile. So for this one, we want to find the z value that has 60% to the left. So we use my normal table, and we try and find 60%. It looks like this 59.87 is pretty close. So z equals 0.25. So we need to be 1/4 standard deviations above the average. So x is again the average plus the number of standard deviations times the standard deviations. So my average is 65. My z value is 0.25 because I need to be 1/4 standard deviations above the average, times it by the actual standard deviation, which is 15. And we get 68.75. So what does this tell us? This tells us the 60th percentile is 68.75 points. And specifically, what does that tell you, and why do we really care? This means that if you get 68.75 points, you know you are higher than 60% of the other people. So at this point, you've all taken standardized tests in school or the ACT to get into college, and they always report your scores in percentiles. And this is what percentiles tell you. Number 2. If 10% of the class failed, find the lowest passing score. So it's still asking the same thing, we're just changing the way we ask it slightly. 10% of the class failed. So that means 10% on the bottom, those would be the failing students. And then if you're on this side, then you pass. So we're just asking, what is the 10th percentile? What do you have to get to not be in the bottom 10%? So if we look up 10% on my table, I think this negative 1.3 is technically closer. So z equals negative 1.30. So x equals our average plus the number of standard deviations times the standard deviations. Our average is 65 plus z, which is negative 1.30, times the standard deviations of 15, which is 45.5. So you need at least 45.5 points to pass the exam. Let's do something similar in our next question. If the top 5% get a reward, find the smallest score that you need in order to get the reward. So that's saying, okay, the top 5% get a reward. What score do you need to be then in that top 5%? The problem with that is that's on the right side. We can only look up areas for the left side. So if there's 5% in the right, there's 95% in the left. So let's look up 95% on our table. Look up 95%. It looks like z is 1.65. Notice if you tried to look up 5% because you weren't thinking, what would you get? You would have gotten negative 1.65 due to symmetry. But z equals 1.65. So let's find our x. So my average is 65, and then I want to be 1.65 standard deviations above that. So it equals 89.75. So you need at least 89.75 points to get the reward. So we've learned quite a bit. Now let's kind of throw everything together, mix it all up. In example 49, we have some facts about IQ again. So the average is 100 points. The standard deviation is 15. And the histogram of IQ looks like a normal curve. It's approximately normal. So we can go ahead and use the normal table to find our percentages. So number one, what percent of the population has an IQ greater than 135 points? So this time we have the original IQ, the x's, and we want to go to the percentage. So first we're going to find our z-score. So it's x minus the average divided by the standard deviation. So x is 135 minus my average of 100 divided by my standard deviation of 15. So it's 2.33. So z is 2.33, and I want to find the area to the right of it. If I go to my normal table, I'm looking up 2.33. I can't get that exactly, but 2.35 has an area of 99.06. Oh, but that must be the area to the left. So there to the right would be 100 minus 99.06, which is 0.94. So my final answer is 0.94%. So not very many people have an IQ greater than 135. Number two, what percent of the population has an IQ between 90 and 110 points? So this is similar, but now I'm going to have two z values. So z equals, again, x minus the average over the standard deviation. So 90 minus 100 over 15 is negative 0.66, and z equals x minus the average over the standard deviation. So 110 minus 100 over 15, that's going to be positive 0.66. And now I'm looking for the area in between, so negative 0.66 to positive 0.66. So remember, to find the area in between, we just find each of the individual areas and subtract. So if I look at 0.66 or 0.65, that seems to be the closest, so 74.22 minus, and now look up my negative 0.66, so 25.78. This gives me 48.44%. So about 48.44% of people have an IQ between 90 and 110 points. Number 3, what is the minimum score I can get and still be admitted into Mensa? Well, Mensa only admits people with IQs in the top 2% of the population. Thus, to be admitted to Mensa, you have to have an IQ in the 98th percentile, at least. So this one is one of the problems in reverse. So we want to be in the top 2%, which means there's 98% over here. So we need to find the z value that will put us in the top 2%. But because our table only uses areas to the left, we're going to look up 98%. So look at the areas for 98%. Oh, this one's actually really close. Of z equals 2.05 for an area of 97.98. So z equals 2.05. Now we need to change back to an x. So x equals our average plus the number of standard deviations we are times the actual standard deviation. So x is going to be 100 plus 2.05 times our standard deviation of 15, which is 130.75. So you need at least 130.75 points, IQ points, to get into Mensa. And number 4, what percent of the population has an IQ of less than 75 points? So this is the non-reverse, where we know what x is and we try and then figure out the percentage. So let's first find our z. Z equals x minus the average over the standard deviation. So x is 75 minus the average of 100 divided by our standard deviation of 15. So negative 1.66. There's my negative 1.66. We want the area to the left because we want the IQ of less than 75 points. So we go to our normal table, look up 1.66. Looks like that area is 4.95. So my final answer is 4.95%. And just as the final caution, again, not all histograms are normal. And we can't use the normal histogram to figure out areas or percentiles if the histogram doesn't follow the normal curve. Sometimes we can see that the histogram isn't normal because the normal curve would give crazy answers. So for example, if we use the normal curve for incomes, and remember incomes usually have a really long right tail because there's only a few people that make a really high salary. But if we use the normal curve, it would tell us that we had a large percentage of people that make incomes below 0, which doesn't make any sense, so that would be a crazy answer. For example 50, GPAs for a group of students have an average of 3.5 and a standard deviation of 0.5. Does the histogram for these GPAs follow the normal curve? Well, if it did follow the normal curve, then you'd be centered at 3.5, and then if you go up one standard deviation in either direction, that would be a 3 and a 4, and that should be the 68% of the people between one standard deviation. And then if you go up another one, that would be 4.5 to 2.5. So up 2 SDs, negative 2 SDs. And that should be 95%. But wait, that doesn't make any sense. It can't look like this because GPAs stop at 4. It doesn't make sense for it to be centered at 3.5 when it only goes to 4. So the normal curve doesn't make sense.